Welcome to this puzzle session. Today we'll be discussing a very classical problem. So fix a positive integer n and suppose s is a subset of the first two n integers such that the size of s is n plus 1, which is more than half the size of that. So we have collected some n plus 1 integers from the first two n integers, and now the conclusion is that there exist two distinct numbers in S such that one of them divides the other. So it's very interesting. Just by this constraint, one can show that there exist two distinct numbers in S such that one divides the other. As usual, one is encouraged to pause the video and try to solve the problem oneself before looking at the solution. And now let us look at the solution. So first, forget about the problem and consider these sets that I'm defining. So A1 is all powers of 2, including the 0th power. A3 is 3 times all powers of 2. 3 times 2 to the power 0, 3 times 2 to the power 1, 3 times 2 to the power 2, and so on. A5 is 5 times every power of 2, and we can keep going. And here is the simple observation is that the set of natural numbers is partitioned by the AIs. So let me explain what is meant by this equation. This means that every natural number is in one of the AIs and exactly one of the AIs. That's what this means. Why is that? Because if you pick a natural number m, then you can write it as 2 to the k times some odd number, right? There is a unique k and a unique odd number such that m equals that. And whatever is that odd number, let's say it is 5, then m is a member of A5, clearly. And with this, one easily includes this equation that every natural number lies in precisely one of the AIs. All right, and an immediate consequence of that is the following, that S is A1 intersection S, A3 intersection S, and so on, A5 intersection S. Why is that? Because, well, if these things partition N, then their intersection with S partition S. Every element in S will lie in exactly one of these folks. But note that this actually we can stop at a finite point, at which point it stops is this one. So we do not need to go beyond any of these because A2n plus 1 intersection S is empty. Why? Because A2n plus 1 is disjoint with the first 2n integers. Right? There is no element here which is here, and therefore there is no element here which is here, or in S in particular. So S is partitioned by these sets, and how many of them are there? These are n of them, right? These are total of n sets. Now the size of S is n plus 1, and the elements of S are put in n boxes, so to say, and therefore by common sense or pigeonhole principle, it follows that thus there exist, this is the symbol for there exist, two different integers. Let us call them maybe P and Q in S. So all this says is that there exist two distinct integers P and Q in S such that P and Q lie in AI intersection S for some I. So this is a complicated way of saying that two distinct integers in S fall in a common box. That common box is this. But note that whenever you pick two different integers in some AI, let's say you pick two different integers in A3, this one and let's say that one, then the smaller one divides the bigger one. So that's why these partitions were made. Whenever you pick two things in any of the given AIs, the smaller one divides the bigger one. So now since P and Q are two distinct integers in a common AI, they are in AI intersection S, and hence in particular in AI, whichever one is smaller divides the bigger, and hence we have found two distinct integers in S such that one divides the other. So that's a beautiful proof of a fairly non-trivial fact. I will post a link of a Stack Exchange thread in the comments, sorry, not in the comments, in the description. You can check that. It has interesting discussion and other proofs. So with that, I want to end this lecture. As usual, like, comment, share, subscribe. I also have Patreon. The link is in the description below. Thank you for listening, and I'll see you next time.